Good evening and welcome to your third video of our Chapter 7 series. Tonight we will be using those formulas you learned to write last video to get some more information from them. Once again, you will need your pink sheet handy along with a calculator. So let's look at molar mass. If we remember, molar mass is a unit of grams per mole. So we're going to now look up the molar mass of our compounds instead of just an element. So to do so, we're going to look up individual masses and we're going to add them up. If an element has a subscript after it, we need to multiply the mass by that subscript before we start adding it up. Now, there are a few elements you got to be careful of, and these are our Hofbrinkel elements. These elements that when they are by themselves will have a subscript of 2. So if we talk about hydrogen gas, well, hydrogen bonds with itself to make hydrogen gas. So it would have a subscript of 2. So we need to start looking out for these as we go through problems. Elements, of course, then are all in the name Hofbrinkel. So we have hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So let's just watch out for those as we go through into further chapters and a little bit further into this video or this chapter. So let's begin by looking at an example of barium nitrate, or BaNO3 What we're going to do is we're going to look up the individual masses. Remember, when we look up the mass, we're going to round it to the nearest whole number. So the masses that I'm going to write are going to be those rounded masses. So when I look up barium, barium is 137 grams per mole, putting in our units. Nitrogen is 14 grams per mole. Now we got to be careful with nitrogen. Nitrogen is in this set of parentheses here. So what this means is this 2 is going to distribute to both oxygen and to nitrogen. So nitrogen actually has 2 of them. So we're going to take our 14 and we're going to multiply it by 2 and get 28 grams per mole. Then we have oxygen. Oxygen has 3 already, but we need to multiply that by 2, so you're going to multiply the subscripts. So oxygen is 16 grams per mole, but we're going to multiply it by 6, because we're going to take these and we multiply them together when we distribute. So 16 times 6 is 96 grams per mole. And now all I need to do is take these 3 and add them up. So you plug them all into your calculator. And we get 261 grams per mole. Let's try 2 more here. CaNO3 So we're going to look up Ca, and Ca is 40 grams per mole, and we only have 1 of them. Then we have NO3, but remember we have the 2, so the 2 is going to distribute through. So our N is 14 times 2, which is 28 grams per mole. And then we have our oxygen, which is 16 times 6, which is 96 grams per mole. And then we just add them all up so that we get 164 grams per mole. What about a polyatomic ion? Because it's still a formula, but it just has this -3 out here. Well, the -3 talks about electrons. And what do we know about electrons? Well, electrons are very small and they basically have no mass. So they're not going to add to this formula at all. So if you're doing one that has a negative or positive charge, basically we're going to forget about it. So we look up phosphorus. Phosphorus has a mass of 31 grams per mole. Oxygen is 16 times 4, because we have 4 oxygens. So that is 64 grams per mole. We're going to add those up, and we get 95 grams per mole. So hopefully you had an idea of how to do this already, and this was just a little bit of review. So a little bit more review back from chapter 3 that we're going to see play into this chapter is converting from mass to moles, moles to particles, and mass to particles. So remember, when we are going from mass to moles, we're going to take our grams divided by the molar mass. Or we used to see it as grams times our line, our molar mass on bottom, and 1 mole on top. So we were changing to moles. So our grams would have canceled with our grams down here. We would have been left in moles. So molar mass, again, we look it up and add up this time. So we're just going to take those grams divided by our molar mass. When we were going from moles to particles, we had moles times 6.02 times 10 to the 23rd, which remember is Avogadro's number. And again, when we did it, it looked like moles times a line, 1 mole on bottom, and then our 6.02 times 10 to the 23rd on top. So moles would have canceled. We would have been left with particles on top. So you can see we're taking out this 1 because 1s really don't change anything in our calculations. And then of course if we wanted to go mass to particles, we took our grams, multiplied it by Avogadro's number, divided it by the molar mass. So we had grams times a line. To get rid of grams, we would have the molar mass on the bottom, Avogadro's number on top. So we want to know, what is the mass of 2.5 moles of oxygen gas? So we look up what we're trying to find, and we're trying to find mass. And then we need to know where we're starting. So we're starting with 2.5 moles of oxygen gas. Oxygen. Oxygen is one of those Hofbrinkel elements. So we need to be careful of that when we do our oxygen. So we're going to start with 2.5 moles of oxygen. So oxygen will be O2. It's Hofbrinkel, it gets a 2 because oxygen is by itself. Times the line, moles on bottom, to cancel it out, mass on top because that's what we are looking for. So we need to look up the molar mass, and oxygen of course is 16, and we have 2 of them. So that is 32. 2.5 times 32 gives me 80 grams of O2. Let's try one more example. How many moles of NH4,2SO4 are in 6.60 grams? Of course, we know NH4,2SO4 is ammonium sulfate. At least I hope you do. If not, go back and review your naming rules. So again, we want to know, what are we looking for? So we're looking for moles. And then where are we going to start? we're going to start with 6.60 grams. So 6.60 grams of NH4 to SO4, and we're going to times the line. Now we know we're going to take grams and put it on bottom. So what we need is the molar mass of this. So N, as 2 gets distributed through, I have 14 times 2, so 28. Then I have H, which is 1 times 8, because remember we multiply the 2 subscripts together. So that gives me 8. Then I have S, which is 32. And I have oxygen, which is 16, but I have 4 of them, so 16 times 4. So there would be my molar mass. All I need to do is add them up. So this gives me 132 grams in 1 mole. So my grams will cancel, and I am left in moles. So 6.60. I'm going to divide that by 132. And I get 0.05 moles of NH4 SO4. So again, same as we were doing before, all we're doing is getting a little bit more complicated with our molar mass. Last example, how many molecules are in 125 grams of copper 2 nitrate? So what are we looking for? Molecules. What do we have? Grams. So we always start with what we have. So I have 125 grams of copper 2 nitrate. Well, since I have to get some numbers, I need to convert the name into a formula. So we know copper is Cu. This 2 tells me I had copper plus 2. Nitrate ends in 8, so I look it up, and it is NO3, and it's got a negative charge. So then we're going to crisscross our charges, and we're going to get the formula CuNO3 2. Again, NO3 in parentheses because we're going to need 2 of them. So I have 125 grams of CuNO3 2. And I'm going to times the line. Grams has to go on bottom. And then I put my molecules on top. Well, molecules is always Avogadro's number. For grams, I gotta, again, look them up and add them up. So copper is 64. Nitrogen, again, distributing your 2, is going to be plus 14 times 2, which is 28. Plus O, which is 16 times 6, which is 96. Add those together, gives me 188 grams. So now when we do this, we're going to take 125, we're going to multiply it by 6.02, and remember you can use that E button for your times 10 to the 23rd. Remember, when you use your EE button, you take out the times 10 and you substitute it with the EE. So it would be 6.02, your EE button, and then 23. And then you are going to take that and divide it by 188. And we are going to get 4 times 10 to the 23rd molecules of CuNO3 2. So hopefully that has given you a little review of how to do all those different conversions that we did back in Chapter 3. If you need a more complete explanation of how to do these, look back in those Chapter 3 videos. So our new thing we're going to look at is percent composition. So we're going to take a formula and find out what percent of that formula each element contains. So in definition, it is the percent by mass of each element in a compound. The formula you're going to use is taking the molar mass of the element and dividing it by the molar mass of the compound. And then, of course, because it's a percent, we're going to multiply it by 100. So we're going to find the percent composition of Cu₂S. So how do we begin? First thing we're going to do is find the molar mass of the compound. So Cu has a mass of 64. We know there are 2 of them, so we're going to multiply it by 2, and we get 128 grams. We're going to add that to S, which is 32, and we are going to get an answer of 160 grams per mole for the compound. Once we have the compound's mass, we find the percent of each element. So we're going to take the total mass that element contributed to the formula and divide that by the total formula mass. So for Cu, I am going to take 128, not the 64, because I have 2 of them. So I want to take the total that it gives to the formula. So I'm going to take 128, divide that by 160, and multiply it by 100. And that comes out to 80%. Well, that should mean sulfur is 20%, because we can only have up to 100%. So let's double check ourselves. Sulfur would be 32 over 160 times 100, and indeed it does come out to 20%. Let's find the percent composition of BaNO3 2. Mass of Ba, 137, plus N, which is 14, times 2, which is 28, plus our oxygen, which is 16 times 6, because again we distributed that 2, which is 96. Add them all together, and we got 261 grams per mole. So now to find the percent composition, we're going to take each element individually. So for Ba, I would take 137 over 261, multiply it by 100. So I get about 52.4%. Then I'm going to break up NO3. Because I want to find the percent composition, I'm going to break it down. So we're going to take N individually as 28 over 261 times 100, and we get about 10.7%. And finally, for oxygen, we would get 96 over 261, multiply it by 100, and we get about 36.8%. Now, if I wanted to know the percent nitrate, I could do that too. Just combine the 2 masses of N and O and take that over the total also. So sometimes we see weird formulas like these. These are called hydrates. And we often want to know what is the percent of water in this hydrate. As we do this, we're going to do it the same way, but we're going to focus on one part only of the formula. Now we have this dot here. That just tells me that for every zinc sulfate, I have 7 waters. What I'm going to do is just add the 7 waters to this formula. I'm not going to multiply it. A lot of you will make that mistake and try to multiply because the dot often seems like multiplication. But this is just a way to show a formula is a hydrate. So let's begin by just getting the mass of the formula. Zn is 65. Adding it to sulfur, which is 32. Adding it to oxygen, which is our 16 times 4, which is 64. And then we're going to add it to our waters. Since I want to know the percent of water, I am not going to break this down into hydrogen and oxygen. I'm going to leave it together. So I know I am going to need the mass of that. So I need 7 times my waters. So hydrogen is 1 times 2, or 2. Oxygen is 16. So 2 plus 16 is 18. Now I'm going to take that 7 times 18 and get 126. So to find my formula, I add all of these together and I have a total mass of 287. So again, wanting to find the percent of water, well, this is water. So I am going to take 126 over the total 287, multiply it by 100, and I get 43.9% water. So we used part of the compound instead of all of the elements individually, and questions may ask you for that. But again, do the same thing. You totally need the mass of everything and then break it down for what they're looking for. What if we're given the percent? So we're going to work a little bit differently when we do this. So we know magnesium hydroxide is 54.87% oxygen by mass. So it's saying in the whole formula, I have 54.87% oxygen. I want to know how many grams of oxygen then would be in 175 grams of the compound. So I know my compound has a mass of 175 grams. I know 54.87% of 175 is oxygen. So how do I do this? I'm going to do straightforward math. I'm going to find a percent of a whole. So when we look at this, we change this into 0.5487, and then of means to multiply. So what I've done is I've taken the percent, so I take 0.5487, multiply it by 175, so I know I have 96 grams of oxygen.